Hello all, welcome. We're going to talk about the ratio test right now. The first thing about the ratio test that we want to talk about is we want to find the limit as n approaches infinity of our second term over our first term. And so we want to make sure that once we find that limit, our really care is what this r is. If the limit actually exists and the value is less than 1, just like a geometric series, then we're going to have this series converge absolutely. When I talk about the alternating series test, I'll talk more about what absolutely means versus converging conditionally. If the r, when we take the limit, is greater than 1, then that means the series will completely diverge. And if it's equal to 1, then the test is inclusive. Just basically means that we didn't use the right test. So I've got two examples that we're going to do here, and I'll start with example number 9. And example number 9 says that we're looking for the sum from infinity, where n is equal to 1, of 2n over n factorial. One of the things that's really helpful in maybe using the ratio test is when we have factorials, we have numbers raised to a power n or an n plus 1, just like we do right here. So we're going to go ahead and look at the question and see what we can do with it and see if we can figure out what's going on. So in order to solve this problem, the first thing we're going to do here is we're going to write the limit as n approaches infinity. And we're going to do the second term first, or the term that follows this one. So this is going to be 2 to the n plus 1, right? If this had been 3, so 2 to the third, well, this would just be 2 to the fourth. This will be our term for this. And then instead of being n factorial, we're going to do n plus 1 factorial. And we're going to divide this. We're going to divide this by the actual term we have right here, which is what we see right here, right? This a sub n. And so this is going to be 2 to the n all over n factorial. And then we're going to do the absolute value of this right here. And we're looking to see what this actually equals. We want this to equal some r. And the r is going to tell us whether the series converges or diverges. So this will be the first and last time that I write it like this, because as we all know, that if I'm trying to find the limit of something, of a fraction of a fraction, I can rewrite this as the limit as n approaches infinity of 2 to, I might go ahead and also rewrite this. So 2 to the n plus 1 is the same thing as 2 to the n times 2, right? If I were to add, this is really to the first power, right? So if I add, but if I multiply these things together, then I'm really adding the exponents. This one's harder for students to see, but n to n plus 1 factorial is actually n factorial times n plus 1. And then I'm going to go ahead, and when I'm dividing by a fraction, I'm actually going to multiply by the reciprocal. So I'm going to go ahead and do this. And again, I'm going to go with the absolute value of it. So what's really cool about this is that I'm now able to start simplifying things. So remember, all these things at the top, all three of these things will be multiplied together, and then these three things at the bottom will also be multiplied together. So that way I can go ahead and eliminate the 2 to the n's, and I can go ahead and eliminate the n factorial. Because I'm trying to find the limit to this thing, right? I need to know what this limit is. And it's really hard to figure that out without using L'Hopital or just some other crazy method. So my goal is to actually try to figure out what I need to do with that. Okay, so now with that being said, I can go ahead and do the limit as n approaches infinity, and then at the absolute value of, well, the only thing that's left in the top is actually just 2, and the only thing that's left in the bottom is n plus 1. Well, this is a very easy limit to find because you can see this is a bottom heavy function. Therefore, this limit is going to be equal to 0. And since this limit is less than 1, right, so this is our r value that we found in our equation. It's right here, right? That's the r value. So in this case, we get to the 0. And so our limit is equal to 0, which is less than 1. Therefore, I can now conclude that this series is going to converge absolutely. Okay, absolutely. All right, so hopefully that makes sense for this question. It's pretty straightforward. And let's go ahead now and look at example number 10. All right, so for question number 10, we're going to find the limit as n approaches positive infinity of n plus 1 squared. So I'm going to go ahead and do the second term, the following term first. And then this is going to be 2 to the n plus 2. all over 3 to the n plus 1. So basically I'm adding 1 to my exponent for all of these things right here. And then I'm going to go ahead and divide by the reciprocal of our denominator, right? The denominator of what's right here. So I'm going to go ahead and divide by the reciprocal of that. So it would be 3n, n squared, 2 to the n plus 1. I'm going to take the absolute value of this. And this really kind of, once we talk about the alternating series test, this kind of makes more sense of why we do the absolute value of this. And again, we're going to set this equal to some value of r. And again, we're looking for the value of this. If it's less than 1, it converges. If it's greater than 1, it diverges. And if it's equal to 1, then we've chosen the wrong test. So, all right, so let's look at the next part of this problem and see what else can we do. So the first thing is, let's just kind of like actually break these things apart. And so I'm going to go ahead and factor out the n squared plus 1. And I get n squared plus 2n plus 1. And just like we did with the previous example, I'm going to go ahead and do the 2 to the n. Now, those students mess this up. So it's 2 to the second, right? So it's 2 squared. So just don't think that this is going to be in 2. And then we're getting 3 to the n. So if I actually simplified the top part pretty well, and then down, right down here, I'm going to do 3 to the n. I'm going to do times 3 to the 1. And then I'm going to go ahead and do n squared. And then 2 to the n times 2. So all these things right here are being multiplied together. So I can go ahead and break this part up the way I want to be able to do this. So with that being said, I can now start canceling things out. So 2 to the n cancels out with 2 to the n. 3 to the n cancels out with 3 to the n. This 2 actually cancels out with this, becomes 2 right here. And then I think we're good to go. So let's actually show you what this ends up being. And I should have the absolute value on this, but it's not going to really matter towards the end here. So let's go ahead and finish this problem up. So the limit as it approaches infinity, at the very top I have a 2, right, just a 2, and then I've got the n squared plus 2n plus 1. And on the bottom, I've got a 3n squared. And so this is a very easy limit also to find as approaching infinity, because you can see that the highest number in our numerator, or highest degree rather, is actually an n squared. If I were to distribute that, I would get 2n squared. And then the bottom, I am left with 3n squared. So this actually approaches 2n squared over 3n squared. So this limit is actually just equal to 2/3. And again, this is the r value that we're trying to find up here. And so since this r value is less than 1, I can now say that this series also converges. Absolutely. Okay, so that's a very short version of the ratio test. It's, like I said, very, very important when we start talking about intervals of convergence, and we will do that a little bit later on. So I'll see you guys in the next video.